Today's seminar is about zero knowledge. It's not about a specific paper, but rather about the overall description of zero knowledge proof. Explain and prove detail about some zero knowledge proof. So today's seminar title is From Zero Knowledge Proof to Publicly Verifiable Secret Sharing. First, let's talk a little bit about stability and security in cryptography. Stability in cryptography is originally a peanut trait. Oops, sorry. Stability in cryptography is originally perfect secrecy, which means that even if an attacker has infinite computational resource, no information can be obtained from the ciphertext. However, in public key cryptography, there is a public value, so if you have an infinite computational resource, you can get information from the ciphertext. At this point, public key cryptography has become so prevalent that it has redefined its security contents, limiting its scope to polynomial-bounded computational resources that are semantic security and not infinite. As you know, mathematically, public key cryptography can be solved into any some unlimited computational power. So we talk about how to mathematically prove this semantical security. Uh, uh, Before we explain that, let's talk about indistinguishable. Indistinguishable. This picture above is a Turing test, as you know, a test for evaluating AI. When a person asks a machine and person to correspond A and B with same question, if person C receives the answer from A and B, and if a person can't distinguish which one is from A and which one is from B, that we can say the A same AI have intelligence equivalent to that of a human being. It is known as Turing test. In this respect, even in cryptography, ciphertext, public key, and pre-existing info, and ciphertext without and if indistinguishable satisfies semantic security. In short, very rare information is available from ciphertext. Below mathematical sentence means same means with upper pictures. This indistinguishable is also brought to zero knowledge proof, which is said to satisfy the zero knowledge security unless the actual prober and verifier can distinguish between the interacted transcript and the simulated transcript. I will go back to the more detailed explanation later with an example. So, uh, maybe you have been seeing this property that is well known as zero knowledge proof property. Therefore, if you summarize the above property, they are defined by these three properties. The completeness and soundness above are taken from the interactive proof system. Completeness means that if a statement is true, the honest prover should be able to convince the honest verifier. And soundness means that if the statement is false, no dishonest prover should be able to convince the honest verifiers that this statement is true. The terminology here is that if statement is true, the verifier must know nothing but the true nature of the statement. This is Alibaba cave problem that show terminology proof problem. The situation above wants to prove that P knows the password passing through the screen between cave without giving V any information. P entered the cave with A or B enter and call V to cave. Then we command to come out to P from A or B. If P is correct, he has a half chance of knowing the correct answer. However, if it succeeds 10 times and 100 times and 1000 times, it can be said that P really knows the answer except for a very small probability. V knows nothing but the fact that P knows the answer. For each attribute, the prober can continue to respond to the verifier's request and convince it to know the key. Soundness shows that if the prober does not know the key, one of the verifier's multiple requests cannot be satisfied because it is stochastically wrong. There is no information about some door key other than the fact that you know the key no matter how many times you repeat the some challenge. Among the other zero knowledge proof examples are stock and finding Waldo, which have been prepared for the most institutes. And today I represent a familiar Hamiltonian cycle. The graph G and H above are homogeneous graph. No, homogeneous is not. Isomorphism graph and Hamiltonian cycle can be thought of simply as one stroke draw root. Proper knows that it is possible to draw a line in one time for a given graph and only want to convince him that he knows the answer without revealing it, the answer to verifier. Here is how you can do it. First, create a isomorphism pi that make homogeneous graph G prime from graph G. Then we create a vector like this and the information matrix for G prime. and give these vectors to verifier. And then verifier send challenge 0, 1, 0 or 1 to prober. If prober receive the challenge 0, then prober send a pi function that transforms g to g prime to see if a normal isograph is created. And if prober receive c equals 1, then send to verifier one stroke solution for G prime. If you repeat this process many times, you can say that you know how to draw a stroke in similar way to the Alibaba K problem. Next example is go deeper and look at the example to prove that we know the value of discrete log problem, which is used a lot in cryptography. In other words, we want to prove that P knows S satisfying T equal G upper S. At this time, the above parameter condition is satisfied, prime P and Q such that Q divides P1 and G is generator and so on. At first, P first draws a random number R and sends X to G, which is G upper R mod P. Then we send C the challenge value and P send R plus SC based on the C, on that C. And then we then check that Y power of G and minus C power of T are the same as the original X, and if they are the same, we know that S corresponding to T equals G, S power of G. In the case of Alibaba, the value of C is only 0, 1, 0 or 1, so P has a probability of knowing and manipulating it, but it with half probability, but here is C range is 2 power n 1 over 2 power n. But the disadvantage of GK proof is introduced so far is that both P and V are available when they are online. The zero knowledge method introduced here is a non-interactive method with goal of minimizing the interaction between P and V. This is some about the Shinoru identification protocol, which aims to prove that probers does not release private key to verifier. It may look similar to the previous protocol, but the biggest difference and the key is the value of E. E is same with C in the previous protocol, which was originally chosen by verifier C, which delegates each role to the hash function. Use the hash function as a random oracle based on the prober's ability to control it. Now here is to show it proves for equation, but it is almost same before protocols. So this and this shows the prober knows the private key without reveal the private key. Similarly, if we apply the above protocol to general knowledge property, we can derive an expression that satisfies x equal x prime unconditionally by prober who knows private key. Also, if the prober does not know the private key under bounded computational resource conditions, it is impossible to produce a value that satisfies x equal x prime. Also, verifier can't get any information other than private key. Then we talk about how zero knowledge proof was actually used in the last I introduced PVSS. Before that, I reviewed the secret sharing and verifier secret sharing and some public verifier secret sharing. Secret sharing is a method by which dealer creates a secret value and then propagate the partial value to several people and recover when a certain number of partial values are collected. In the example above, it has been propagated to 6 people and the 4 values can be decrypted. As a method, dealer creates a polynomial of size t-1 that is required for recovery. And in the case of 4 people, we are going to create a third degree polynomial. From there, the value of 0 in px, that is a0, become the secret value, and p1 to p6 corresponding to n1 to n6 is calculated. The dealer then passes p1 through p6 to each to n1 to n6, and each of n1 to n6 will share their pieces they received with each others. The shared fragments are used to recover the polynomials and p0 to recover the secret. This is our secret sharing method. Then the question arises here. For example, if you think about node 2, I got P2 from dealer and I don't know if it's a real P2 value. There is a problem that you cannot know whether P2 is from PX. So dealer also makes CJ when making PX, where AJ is the coefficient of x power of j and define xi as the following and sends cj with p2. And you can make xi like this form, and this is some example of x2 in polynomial degree 3. That means t is 4. So so if we if node 1, oh sorry, that is node 2. If node 2 get encrypted 2 and p2, the node 2 can check x2 equal g power p2 value. So if two values are same, that node 1 knows that she he received p2 in normally. But the question in PVSS is whether a third party can verify it. Normally, when you pass data, it is sent encrypted with a public key. Here, N2 who received P2 knows that he or she normally received P2, but no other N1 or N6 or others knows it. This can be proved by releasing encryption key, but this is also not possible since the encryption key cannot be disclosed until P2 is shared. And even if you reveal your cryptographic keys, you will have to recreate them every time later on every protocol. So PBSS use a zero knowledge proof to solve it. Without revealing the P2 value, P2 N2 want to prove only that I receive P2 as normally and I know that value. The zero knowledge proof technique used here is the Chom and Peterson protocol. It's called the DLEQ protocol, which is also based on discrete log problem. Using the property log under G1H1 equals log under G2H2. The proper knows the secret value A and H1 equal G1 over A and H2 equal G2 over A. The protocol proceeds in the following steps to make it easier to understand. Let's use the example below. The left side is the original Chom Peterson theorem, while the right side is a visual representation of the scheme used by PVSS. Here is an example for node 1, not node 2. The secret is P1 and therefore x1 equals g over p1 and y1 is the value of p1 encrypted for public key y1. This x can be found using previous slide like this way, and therefore it is same as the relation of hg on the left. Select the random value w and determine a1, a2, the r equal w minus p1, c, where c use the hash of si, yi, a1, and a2. If you put in a value and then calculate it, if this expression that calculates a1 is equal to gw, it means that you know p1 used in the commit. If you look at the second a2 first, it means that you know p1 at yi. And you can prove p1 in public key and p1 in G and prove that they are the same. This way we can prove that we send p1 for commit to encrypt p1 without sending any information about p1. Going further from what is used in PBSS, we discussed zero knowledge GK snarks, which are now today's mentioned a lot. GK snark is following abbreviation and the rest of the term are known in zero knowledge proof, but difference is and key point is succinct. Non-interactive zero knowledge proof has the advantage that it does not have to be online, but it has the disadvantage of proof complexity. Succinct is added to simplify this. Technologies no, GK Snark has three steps as follows: key generation and verify, uh, proof generation and verify. First, assume that the key generation is, for example, a secret value W and a program C that proves the prover knows the W. Generator G puts this program C and lambda, and the prover must not know the lambda. Because if prover knows the lambda, then prover can create fake proof for some secret W. So prover must not know about the lambda. The result is proving key and the verifying key. The prober calculate PRF and then pass only PRF to verifier. The time it takes to compute PRF is long relative to the magnitude of the inputs X and W. After PRF is computed, of course, we can't deduce W from PRF, and PRF's length is very short. The verifier receives the PRF from the prober and executes the verifier algorithm V to determine the authenticity of the PRF. Verifying tasks, verifying takes a very short time, which is one of the features of JK snarks. It can be used as a blockchain scalability. Many attempts have been made to solve block scalability using JK snarks. Corda protocol is one of them. Client participating in the blockchain can quickly verify that the contents of the block have not been tampered with by seeing the proof of the full node even if they do not actually know the contents of the block. Eventually, this will dramatically increase the block sync speed of clients, allowing new clients to quickly join the network. And Zcash is very famous thing of using ZK snark, and it can zero knowledge proof can be used in many ways as above: ownership, account balance, membership, stock, and so on. Among the studies related to the plasma sidechain of Ethereum, the use of ZK snarks is emerging. One of the biggest obstacles to the steady-state plasma chain has been the difficulty in demonstrating the consistency of the sidechain on the whole chain, which ZK snarks provide a clue. And Vitalik proposed some protocol rule named as rollup. One of the Ethereum's on-chain scaling solution also uses ZK snarks to theoretically extend the Ethereum space by 10 to 30 times without hard fork. In addition to these infrastructure technologies, there are use cases in applications. Starkware is using GK Snark to create a non-custodial exchange solution that does not hold user asset and is currently working closely with the 0x protocol. Since GK Snark is a concept based on cryptography, if the theory itself is very difficult, if you can understand it well, there are a lot of fields that can be applied. And this is about some adapted my some research. And thank you for listening my presentation.